All right. Hi, everyone. Welcome to AI for Developers. We are excited to have you here. Welcome, welcome. Welcome the live audience. Welcome YouTube, LinkedIn. Thank you all for coming. I know the weather is not great, so it shows a great motivation. Thank you all. So first, we are the AI user group. I'm not sure if, who is here for the first time? Who is, okay, oh wow. Okay, cool. All right, so we are AI user group. We do a lot of events, AI events for professionals. Our goal is to train professionals on AI tools. We have three verticals. One is AI for marketers, AI for designers, and AI for developers. If you have any interest in other topics, AI for marketers, AI for designers, we have one event a month on each topic. So please check out. And then starting January, we'll start running workshops on each of this vertical. And we'll start also having hackathons as well. So just subscribe to our newsletter and you'll hear from us when all these events are happening. The agenda for today, we're gonna start with Kobe showing us MLflow and how discover MLflow and the Databricks agent framework. Then we'll hear from David with his talk, how to build enterprise AI search, multimodal intelligence across all AI data. And then Ivan will talk about evaluating Gen AI on Vertex AI. So we are a community. Our talks usually are also coming from the community. You don't need to work for an AI tools to come and present. We are also very interested in people having a workflow, tried something new, learn something new, and want to share with the community. So please come find me at the end of the event if you worked on something. Also, if you worked on something and it didn't work and you learned something from it, it's also very interesting to share. We don't have a lot of talk like that. People are a bit shy when things are not working, but it's actually very interesting. So please let us know. And we are interested in having you on the other side. Now, so we are co-organizing this event with a company called n8n. It's a low-code platform. It's open source. They have AI agent nodes. So if you don't want to code everything, you can use them. And our friend Max will do a quick demo of their tool. Oh, wait. If I don't have the sound.
Automation platform, technical teams. In this example, you're seeing I've got some nodes on my canvas. Each node executes and passes its data along to the next node. What I'd really like to show you is our new advanced AI functionality. In this example, I've created an AI assistant that helps me interact with my Google Calendar and lets other folks book an appointment with me. So how this works in a nutshell is this agent has various dependencies that it needs. It has the LLM itself. It has some memory so it can handle multiple conversations at once or multiple threads in the conversation. And then it has various tools to understand how to fetch availability in my calendar and to book that appointment. So let's do a quick example demo of this, and then we'll see how it works. So let's see when Max is available next Tuesday. So what my AI agent is doing now is it's understanding that I'm asking for availability, and so it's using the tool to fetch my availability. The agent knows when today is, so it knows when next Tuesday is, and here now it's listed the various slots that are available. Let's book something for 4:30 p.m. Okay. And so my agent is still running at this moment. Great. So the agent, before it makes this request, it understands that it needs my full name and email to complete the request. And so let me specify that. So now that the agent knows that it has all the information that it needs to make the call, it can book the appointment on my behalf. Great, we can see we've got a confirmation here. And if I check in my calendar, we see at 4:30 p.m., we booked that appointment. Now, let's see what's happening under the hood. So my chat trigger here is collecting the responses from myself and sending it along to the agent. This is an arbitrary step, right? So this could be a webhook trigger, this could be your own custom trigger that you've coded. That really can be anything that you'd like. It pipes the message into the agent, which then interacts with its various tools. In the agent itself, I have a system message. I'm letting it know that what its task is, and I'm also giving it what today's date is, and that appointments are also 30 minutes. I myself am not a prompting expert and wrote this rather quickly, so you don't have to be an expert to start getting value from this. And then the magic really happens in these HTTP request tools. So each one of these tools allows my agent to consume an API endpoint and understand how it works. So we've got the get calendar availability tool, and we've got the book appointment tool. So setting one of these up can literally take a minute or two. As you can see, I've described very simply when it should use this tool. Call this tool to book an appointment in the calendar. I then define the endpoint that it should consume. I define the credential to use if necessary. Since we have Google Calendar credentials in n8n, I'm using a predefined credential type, but I could also use a generic one if it's something like a proprietary system that you're connecting with. And then from there, I'm essentially defining the payload to send in my body. And as you can see here, I've got some static parameters. These are the things that I don't want my LLM to manipulate. And then I have placeholders for the things that I do want it to manipulate. And as you can see, I can blend static text with these dynamic parameters that I'd like the LLM to control, or my agent to control rather. And then if I want to, for added control, I can, for these placeholders that I've defined, I can add some more definition on how the AI should interact with those parameters. So there can be a description, and I could even define the expected data type of that. So again, I'm constraining what my agent does, so we have more predictable outcomes when we ship this to production. So from here, I could add more tools, of course, depending on what I need my agent to do. There's various off-the-shelf tools to understand the world or perform math, etc. I can interact with an arbitrary API endpoint. I could write a tool in code, and I can even call other n8n workflows. So this workflow that you saw over here could be consumed by my agent. We have hundreds of native integrations, so it's a really fast way to get your agent interacting with the tools and services where you have valuable information that your users, customers, etc. might want to interact with. I'm Max from n8n. We've just scratched the surface in this demo, but make sure to check us out.
All right, very cool tool. If you don't know about it, please check it out. Kobe is next.
Can everybody hear me okay? Is this going all right so far, sound-wise? I'm gonna pull this up just a hair. I'm jealous because I actually feel more comfortable walking around than standing just solely behind a podium, but I'm jealous he had that microphone to work with. We're gonna get started. I'm here, I'm Kobe Crawford. I'm a developer advocate at Databricks, and the title on the deck is accurate. I had an opening where we were going to talk specifically about MLflow, and we actually are going to talk about MLflow and the agent framework as sort of an answer to a broader question. But I've got this talk set up in a way where what we're doing, what I'm trying to set up here is just sort of to give a level set for people. Like if you've come in, I didn't have a really solid sense of like exactly where the audience was going to be in terms of like their pre-existing knowledge. I sort of began with the idea of like I'm talking to a generally technical software engineering focused kind of group, and that the AI part might be something that's part of your day-to-day, and yet it might not be. So that's why I'm going to begin with kind of level setting with talking about compound AI systems in general. And then closer to the end, I'm going to pick out a couple of features that Databricks offers that are one way to sort of tackle the challenges that compound systems bring to the table. And I love seeing the N8N demo up front because a lot of the things resonate in terms of like, these are the problems that they're providing a low-code answer to that you don't have to think so hard about in terms of getting that UI set up. Similarly, what we want to do is talk about how we're making certain things easier for you in terms of how you can get things done. So really quickly, just for the sake of this conversation, show of hands, how many people are working with AI tools on the daily right now? Okay, great, fantastic. That's a strong showing. And then for how many people is it something where like today is a day where you're actually starting to explore whether or not you want to mess with AI tools, but you haven't already done a lot of work with them? Okay, so there's a few people in that camp. So hopefully this is, again, not speaking at a level that's trying to, you know, like I'm not trying to be like pedantic or anything like that. So hopefully this comes at a good place for you. We'll see how we do. Since you're here, you already know certain things around generally where AI is going. And one of the things I'm talking about here and introducing this notion of just speaking to the term compound AI systems is just to sort of say that, you know, before this year, most people were focused on and looking at an individual model and saying, how well is that model perform? We were essentially looking for the notion of like a single AI model that could be trained to being so good in a general purpose way that you just need that one model and it could answer all the questions and do all of the conversational or text-based or input-output things, switch to multimodal, all of that kind of stuff in one supermodel. And what's become relatively obvious working in this industry, and I'm sure you have seen, is that the best solutions, as we look into what's going on this year, the best solutions are not coming about because of a single model that has everything baked into it, but rather by the people who are exposing APIs, putting some additional complexity behind that and making a compound system that's actually delivering on the goals and promises of what we see we want out of AI tools. So when we talk about multi-part systems, what are we talking about? How does this break down? That demo that we just saw from the N8N demo was actually breaking down and showing like here are the pieces that are involved, taking in an input. We have a language model that we're working with, and then there are specific tool usages and there's specific patterns that are being funneled through the process so that you actually know, okay, what I want to do is to connect to a calendar, connect to that API and retrieve things. Let the language model turn a text-based request into what function do I need to call and how do I make that API call to get the things that I want. You're familiar with that, that's what we're talking about. Whether you've used frameworks like LangChain or Llama Index, or whether you've used more helpful in terms of UI tools like what you just saw on the screen here. The idea is that you're connecting the dots between I've got an LLM that can do great things in terms of understanding and then generating text that can be useful for me and applying that capability to specific use cases that have been defined as part of your larger system. So that's essentially like the thing that I think there was a little window of time here where there was like people were just kind of continuing to say, for example, look at if you're looking at the leading benchmarks and you're looking at the you know, like which models are ranking higher than others on the leaderboard, LMSys leaderboard or something like this. What you would see on those is that you might have you know, Gemini and Claude Sonnet 3.5 and OpenAI, GPT-4o or o1 and all of these things being directly compared against something like Llama 3.1 405B or directly compared against Mistral or Mixtral. And the question that I always started running into and I wanted to make sure that people were asking was, you know, is this an apples to apples comparison? Why are you looking at a multi-part system that's actually very good at doing its job, but is just the thing behind that API, and you actually don't know what else is in it? and then saying, well, I'm going to deploy this single model and compare how well this model does. And I just think that we kind of need to remind ourselves that even those systems that we're using every day, where we treat them like a monolithic thing, that there's actually the complexity hiding behind it. And at this point now, if you've been working with, say, for example, O1 or Sonnet 3.5, they're showing you, right? They're saying, look, here's the system prompt. Here's the chain of thought that we're encouraging you to go through to get the output back. Here are the data lookups that we're doing along the way. And like all of these pieces that are essentially the compound system that you can build as well. And the idea is just as long as you know what the pieces are, then you can build a compound system as well, and you can tailor it to what your needs are, depending on what your application goals are. And this is the key. That once we understand that, then we can start getting into the space where what we're doing is applying the same engineering practices we know and love from having done software engineering, distributed systems development in all these other places, and get back to like being comfortable that like, okay, I can take the system, I can break it down into parts, I can look at and modularize this thing, and then look at each component, inspect it, measure it, these kinds of things, and know that what I'm getting back is not something that's coming out of a magical black box, but rather something that I've specifically engineered to give me something that I wanted for my application. So that's essentially like, if nothing else comes out, that's the most important thing I want people to remember about where we are with AI development. As marvelous and wonderful and magical as AI is, we can get ourselves back to regular engineering practices to be able to do the things it takes to develop the applications that we want with the reliability and observability and these other kind of things that we've gotten accustomed to looking for in the software development paradigms. So here we are, breaking down like we thought about this as like a simple static model before, and now let's talk about like the pieces that go into making something happen, right? So if we talk about just looking at individual models and we talk about the notion of prompt engineering, you've been feeding data into the prompt and then making choices about that, and then tweaking the prompt to tell the model, hey, no, I really want this response to be just like this, and can you please not say anything about that other thing over there, and so on, and adding that into the prompt. You can start thinking about RAG systems, and you start thinking about, like, in essence, that next step of we're going to retrieve documents and then insert the document content, the document chunks, into the prompt. So it's like a document-based prompt engineering. And then you can go farther into the space of talking about what agents are doing. And my favorite sort of shorthand for what agents are doing is that they remember state. And as you ask an LLM to generate something back, the LLM's pattern, its behavior itself is stateless, so you actually have to have that. So just even doing a chat interface that remembers the rest of your conversation, you're inserting state, that's an agentic kind of behavior. And then you're just asking the LLM to be the one to generate the next steps given the state space that you're in at that moment. So now you can say, hey, LLM, it's time for us to generate a function call. And you can do other things that are in this kind of space. And that's all still essentially like, remember where you've been, format the response in the way that I like, that's prompt engineering. Get the things that I need for the next step of this process, that's the agent remembering the current state of affairs and having a sense of the flow that you want to get through. So that's it. This is Compound AI. This is just a way to talk about and remind people of what the pieces are that you've been working with already. So why do we care? Like, why think about this in terms of Compound AI systems? Well, one, they work. If you've used the latest models that are out there, you see how good they are. You know, part of how they get there is through adding these multi-part components to solving these problems. What we found working with our customers, this is a set of data or set of statistics and numbers that come from a specific interaction that Databricks had with one of our customers. They started trying to solve a problem. The company's called FactSet, and FactSet has their own query language. They call it FQL, because FactSet. And when their employees get started, or when people who want to onboard and use FactSet come on board, the first thing they have to do is learn FQL and start getting functional with that querying language. And they decided, well, what if we could just provide a natural language interface instead of FQL to help people get on board faster? And so they started down the experimental path, and this is the experiment, right? So, like, you know, don't worry about the numbers being fantastic yet, but is it going to do anything? Can we get somewhere where we start to see that we can possibly get positive results? So they started out with GPT-4 and they got 55% accuracy. It took 10 seconds on average for those responses to come back. And they're like, okay, well, let's see what else we can do. And working with Databricks, what we said was, well, let's break that down into smaller components and start to look at how we can refine and improve the process that's being done to translate a query into the language that's correct for actually running the SQL query. And that ended up being broken down into a couple of different pieces. So starting with a query processor step, and then retrieving information from the data set, classic vector database interaction, right? You got some embeddings and you can go and do a retrieval step. Then there was an LLM involved in generating some arguments to actually be able to pass in and stuff like this to add and to refine the query. And then the final formula, which includes the arguments that were generated plus some of the data that was retrieved and all of these things in terms of categorizing the query itself and how to frame it up. And not only did the accuracy go up 30%, but the latency went down. And you can accomplish lower latency and ultimately lower cost in a lot of these solutions because when you're tailoring what you're doing with a multi-part system, part of what you can do is say, I don't need that big a model to achieve the same result as using the general purpose, full-featured, very awesome, very amazing general purpose model. So you can then start talking about like developing and training specific models that have been tailored to your need, or just a smaller model in general purpose model might actually be good enough for your task right out of the gate. So these kinds of improvements are available to us, and as we engineer our solutions, then we can take advantage of those opportunities. So this is great. They can accomplish a lot of the things that we're looking for in making our applications what we need them to be. They are able to take care of accuracy issues, and because you can supply context from today and not worry about the fact that the last time the model was trained was 6 months ago. You can do verification steps to start with ground truth and compare it to what the LLM's producing so that you can make sure that you got accurate responses. You can add some safety things, guardrails, and these kind of things. So with those opportunities, however, there are some sort of new challenges, some slightly maybe unexpected things start to happen where you think about new kinds of ways of that things can be inaccurate. And on a step-by-step basis, when you have a compound system, where did that inaccuracy come from? So if you start thinking multimodal and you have an image like this come up in response to the prompt, this is the prompt says, generate an image of a Viking, and then these images come back. And you have to say, that's not a Viking. So how do you catch that? And what part of the system is essentially going to be the part to look at to make adjustments to account for that? And so that's going to be one of the things that you want to think about now that we're thinking about a more complex system because it has more moving parts. So part of getting more moving parts to work better is to figure out places and ways that you can automate the kinds of improvements that you need. So DSPy is an open source library. Stanford NLP department published it and it's available on GitHub. I'd be happy to share links for all this stuff. We'll make sure to have that in follow-up materials after the event. And the DSPy library's job is to automate the notion of prompt engineering by using a code style pattern for actually doing that work. So here, this is some Python code that you can write to implement a retrieval system. And what you're telling the code is, I've got a signature for a prediction here. So this predict call, basically the signature is just telling you I'm going to be a question is going to be provided and I need a search query to be the output result. And you just sort of define those at that level in this text-based way. And then if you're familiar with training models and you see it literally using the function call as the name is forward, it really, you can see like the way that they wrote the code, they were reminding themselves of like thinking about like a pattern where with training models, you iterate and you get some kind of score, you compute some kind of loss, and then you use that loss to say which way do we need to tweak to improve. So the same thing applies to how it works. So what DSPy does is automate and uses sort of like what you call a compilation process to find and generate sort of an optimal prompt for a given model. But you can optimize that prompt for that model in a code-based way so that, like, say you swap out a new model, when you get to that next model, you don't actually have to change anything about your code to re-optimize the prompt for the new model, since, as you know, different models have different idiosyncrasies. You run into like slight behavior differences between models, and that could be, talk about like you were using GPT-4o Mini today and you want to try Claude 3.5 Sonnet, so you switch it over. And that's something you want to be able to do without necessarily having to write a lot of code changes. This is a tool that can help with making sure that your prompting gets improved and optimized without having a lot of code changes. So a couple little details you can see about how this works. The generate query step is what we're looking to get out of this. We do the retrieving part involving the chunking as a standard in the context of a RAG situation. Some more examples that are supplied to say, like, this is the format of the answer that we're looking for, and it's part of how it optimizes what the prompt is going to ultimately be, and then what it'll help make the model actually generate the kind of response you're looking for. The next thing I want to mention as like a tool that helps in this space of working with complex systems is AI Gateway. What we're doing with the AI Gateway is essentially providing a proxy. And that proxy's job is to be able to give you the kind of control of what you want to do in terms of requests in and out to a given endpoint, whichever API you're using, whichever model you're working with, and be able to provide controls, rate limiting. You can do some things around observing what's going on, usage tracking. You can actually log these things. You can use this tool to actually have the ability to sort of do some routing. So for example, you might have the idea that you want your system to be more cost effective by using a lower cost model, when a lower cost model will generate a good enough response, but then evaluate the response that comes back and say, was that response good enough? And if the answer is no, then you could escalate and pass that request to a more expensive model. Question? The question is this low code? So there is a UI element for this so that you can actually enable it through the UI, but we also have an API, so you can actually use code and an API call to get it done. So it's both ways. So this AI Gateway then means, again, back to the idea of like, I had one LLM that I was using for this process and now I want to try the next one because the new hotness is out. You can swap out the model inside the gateway, keep everything else about your application architecture exactly the same, and then be able to do comparison. Is the application behaving better with this model versus that one? So you can start to picture like doing things like A/B testing and other things like that to be able to say, like, I'm going to iterate on my model without changing the rest of my application architecture, and make that easy to do without having any major alterations to the rest of the system. So that's another feature in the idea. The idea is, in each case, how do we preserve the ability to do the modularity we want with building a compound system, and then be able to have the tools that we need to make sure that we can inspect how the work is doing and figure out when we want to make changes and what kinds of changes do we want to make. The next thing I'll highlight in the Databricks platform, and it's really kind of these things all go hand in hand when you use them together, but they're also separable in the way in terms of like seeing the modularity. You can apply what you need where. We have this thing, the AI Agent Framework, and what the framework is about is providing both the ability to deploy the application, deploy a model, deploy an agentic tool capability. So it's very similar, actually, what you saw in the previous demo. The idea is you can deploy a tool, you can actually code up the tool in one place and then have it as an element that you can then refer to in the UI. You have the evaluation thing. One of the things that we've done in evaluation is we've built in a very easy to use LLM as a judge evaluation pattern, so that what you develop in terms of building your system, you can then have the responses automatically evaluated and then given a sort of a golden data set that you would use for testing purposes. You have your eval set. You can automatically rerun all of the testing, all the evaluation against that eval set that you have set aside, and then score each of these components in terms of how your application performance is improving based on what you've changed. And so it provides some of that automated testing things that you've been looking for. And the way the agent eval is working with the LLMs as a judge, it does automate that and give you like some decent confidence in certain areas. There's obviously things that LLM as a judge can't solve on their own, which is why you will also have the ability in the system to surface up a head-to-head comparison between one solution and another for your human users to interact with. And then they can type a prompt in and evaluate what they get back from each of the different things and provide their preference feedback on how it's going. And that's a piece of UI that we also have available. And then this last piece here that's mentioned, this MLflow tracing for GenAI applications, the tracing part breaks down tracing the entirety flow that goes into a given tool or given to a given model. So you can actually see step by step, here was an input that was sent in, the prompt that was sent to a given LLM, here was the response from that prompt. Given that response, let's just say that what it was generating was a JSON blob that you want to send to an API call. When the tool sends the API call, it logs that call was made, and then it logs the response as well. And then it iterates through all of the steps in your, if you want to call it like a chain, it iterates through all the steps in your chain. And then you can look through all those iterations and see, for example, if you're trying to diagnose, where did this thing go off the rails? Where did it stop staying true to the source data in terms of being accurate? You can find that point, and then you can say, okay, yeah, the inaccuracy is here. It's in the retrieval step. We're not actually getting the document chunks that we really want. Let's make sure we tweak how we're doing the retrieval. Maybe we need to do not just semantic similarity, cosine similarity search, but rather we need to also do like some keyword search, mix that in and do a hybrid search instead of just cosine similarity or something else. And you can see what you need to get done based on what each of the steps has been doing. So this is where the tracing provides the debuggability, the observability that you need to be able to manage a compound system. And this is the kind of thing, this is what Databricks is about, is providing sort of like a platform and building blocks that you can use to build and customize the thing that you want to get done. So that's basically it. Now I got really close to the mic and it got loud. Sorry about that, step back. So that's basically it. The idea is that once you're working with these systems, you want to be able to debug and analyze what's going on. And you want to be comfortable that you can apply the same old software engineering that you already know in this context the same way that you had before. And once you sort of can demystify that aspect of it, then you're in a good shape for being able to make the application that you want with the accuracy that you need and be able to verify that you're getting the results that you're after. All right, so that's about it. I've got some screenshots that we can skip to for in the Q&A part if there's an interest and a need, but I would love to get some questions if you have some.
Thank you. Thank you, Kobe. Do we have questions for Kobe? Yes. No, so.
Whoa. So I have a question. So regarding the examples, do you have some kind of code examples or use cases how all this stuff can be used in a proper product or application?
So what I have right here in the slide deck is a couple of screenshots. I did not bring a live demo because I'm a little gun shy with live demos
sure.
that end up going south, but I can pull up a couple of screenshots just to sort of highlight what we're looking at here. So this section here, this sort of notebook style interface is the place where we're inserting actual code to write that's going to become a tool in the system that you can then sort of use and connect to. So once that function's been created, and you can see that they're putting in the example, the two different examples, one was Python code and this one's now SQL. But in each case, you write the code for the tool on one side, And then once you have it available in the UI, you can then select it and use it in your agent-based sort of chain setup. So then the chain interface is something you're going to see a little bit more in a different place, but this is the idea of you can see the tool set up there.
Okay, I see, I see.
So here in this UI, what you're seeing is the tool that you wrote in the first step being added to the users to the playground interface that we have, and there in the playground you're actually setting up for you to be able to actually send in a prompt and then watch the behavior happen. So the playground interface gives you that place, type in a prompt, given that you've leveraged a particular tool that you selected from the drop down, and you can select multiple, and then sort of walk through and see what happens, and see if you're getting the behavior that you want out of the calls. The other nice thing about the playground is that once you set it up in the playground, when you want to get code from that, we have an extraction button for being able to extract the thing as a notebook, so then you have all the code for
Oh, wow,
each of
that's
the
cool.
pieces.
Okay, okay. And do you have something like you showed the slide where there are like different parts of the compound AI system, right?
Yeah.
Where you have the LangChain, Llama Index, or some kind of LLM provider, etc.
Yeah.
Do you have some maybe like such? Maybe I understand you don't have a demo, but like some kind of example of such a system, or at least maybe just like blueprints how that would be built using Databricks.
I guess top of mind quickly, like what I would love to do is in the DevRel team we have notebooks that we've published just to show example code and show things built out in published notebooks, and I'd love to like point you at our DevRel examples and then start from there. So
Cool.
that's notebooks.databricks.com/devrel, and again I'll add that as one of the links to share post event so that you can have it and come back to
That's
it.
great. Okay, thank you.
Thank you. We'll send the link post-event, so we have time for one more question, and it's gonna be you.
Hi. In the agentic systems and the multi-agentic systems, you've mentioned about like some function calling, the LLMs calling functions, and some kind of orchestration. Is it tied into like the Unity catalog in any way? Is there any sense of,
Yes.
the data governance or maybe even features or functions? I mean, can you help me
Yes.
sort of like put it all together there?
Yes. So yes, it's tied into Unity Catalog. Very excited that you mentioned that in the specific, because it's an important element of what we can do in this state is to provide the governance consistently across all the things. So just like when you register a model with MLflow, so the MLflow part, all of the things. So when looking at the Databricks platform, a lot of the pieces that we're talking about here are the Databricks hosted version of MLflow. Now, the functionality is essentially the same in terms of MLflow open source versus MLflow integrated with the rest of the platform. But the reason I mention that is to say that what I'm saying right now about MLflow registering a model, one of the patterns that you have inside of the workflow is that you go through the process of training a model or finding and sourcing a model from Hugging Face or what have you, and then you do a step where you actually register that model, and then its registration, you're registering it into Unity Catalog. And that then gets it in the state where it's ready to be governed and managed by Unity Catalog in terms of access controls and things like this. Some things also become like automatic inheritance from that. So if, for example, you've been working with a particular data set and that data set was used to train or fine tune the model, then the access rules that apply to the data set now apply to the model as well. So it's inherited through the same relationship within Unity Catalog for that. So some of those patterns are things that we have baked into it. And then of course, as the administrators of the instance have the ability to do, you can change through the Unity Catalog interface, who has access and what access rights they have. So the governance part is included.
But at the same time, like functions, do they also have some kind of description? And does the LLM automatically pick which functions can be called? Do these functions also, I mean, I'm sure they must have, they should inherit the same permissions for the data as well. So how that part is tied in?
Well, it's more like you inherit the permissions from the person who writes it. So the access the access rules that the person who writes the function has, that's what will be inherited for a function being written. And then when it comes to the use of that function in the context of a given agentic system that you're building, you're defining the chain, you're defining the flow and the steps that you want to occur in the context of building it. So it's sort of a little bit less arbitrary. Like you actually do define, like, I want this one to be called, and then I want that one to be called, and so on, and iterate on those to get through the steps of it. But it is something that, like, that access is defined in how you build the process and the framework. Does that help?
Sort of. I think it solves a lot of the use cases, but there are some use cases where agents are calling other agents and those type of use cases where if the workflow is not fully defined ahead, I mean, I guess it's an implementation detail, to be honest. Yeah.
I hear you, but to your point, right? One of the things that you'll find is that given an agent that has been defined in the system, if you have access to that agent and you want to set up for, your new agent to be able to call that one, it'll be dependent on whether or not you have access to it at the time you try to implement that and set up that linkage in the system. So that's kind of where you typically sort of see those things come about, because again, once one person has written that agent within the platform, then it's available and visible with the access rules based on their visibility.
All right, thank you. Let's give Kobe a round of applause. Thanks, Kobe. More questions during networking. Kobe will be available. Thanks, Kobe. That's great.
Thank you.
Next in line, we have David. There you go.
Hey everyone, how's everyone doing? Cool, thank you very much, Skirl and everyone for coming here today. I'm going to talk about AI search on data lakes. Brief about myself, I'm the founder of ActiveLoop, was working on the company for the last 6 years. Before that I was doing a PhD at Princeton dealing with petabyte scale data sets. And one of the challenges when we work with Fortune 500 customers and including startups is that when we enter, they have so many different databases, data warehouses, data lakes, all across different clouds, and it's very fragmented to be able to access this data. We're talking to a customer, and there's a VP who had like different reporters. They're like in life science pharma, they have manufacturing business, and they produce a lot of drugs. And there's a simple question, what is my last month revenue? He asked, and they got 3 different answers from different tables across their organization. And the challenge is not only in this big, large organization, but also across many different startups as well, where you have all these different data sources coming from different places, and you need to unify and answer a question, but answering the question itself has a lot of contradictions themselves. What if we can actually connect AI to all your data to be able to answer any question, but in a secure and enterprise manner, where it can understand your domain-specific language and answer instantly the question without going through the business intelligence group and going through a bunch of bureaucracy to bring you the answer. And today, I'm going to actually show you both a demo and also how you can build this yourself as developers using Deep Lake. So here's a demo. What we are asking here, can you summarize me recent breakthroughs in brain edema research? What we did behind the scenes, we have 2 data sets. One of them is OpenAlex, which is about 130 million all published article data sets by scientific community. And another data set that sits on top of Azure is 1.3 million radiology images. This question is very simple. Think of Perplexity. You get the answers, get the citations, and here you go. But what if we can ask a question that needs to cross over 2 different data sets? And here in the example, what it does, it both searches in the OpenAlex dataset and in RAD ImageNet dataset and brings back an answer, validating it every step by not only just giving you citations, but also searching across the images and bringing them as a citation inside the text. And furthermore, what if we go and ask another question, how do these breakthroughs in research apply to my patient data? Imagine I'm in a hospital, I have a lot of patient reports, I want to upload and see, well, how does these patient reports actually correspond to the scientific community research? And here is a simple, I already have prepared kind of PDFs that I drag and drop. But the big difference was happening behind the scenes, and we'll look into the technology behind that. There's no any OCR pipeline. This is directly processed by visual language models that take the embeddings or bag of embeddings in this case, now compare against the database you already have and bring the final answer that summarizes both the textual scientific articles from 130 million research papers, but also the images and also the patient data. And this is like a kind of a proof of concept to showcase how you can build so-called RUGs, but across not just a single data source, across all the data sources you have. So let's talk about the technology that enables this. So we open source Deep Lake about 4 years ago, and so far we got about 2.6 million downloads, 8.2 now thousand GitHub stars, 3,000 open source projects depending on it. Technically speaking, this is the most popular data lake on GitHub that's specialized for AI. But furthermore, we also have enterprise customers, including Fortune 500, that deploy this and manages all their multimodal data currently in production. And what we released about a month ago is Deep Lake version 4. And I'll tell you about that in a bit. So let's take a step back and focus about database theory. When Oracle released their initial database, all the index, all the data is in memory. It works great. You have this low latency, hot memory access. You can ask a lot of questions or queries, SQL queries, and get response back. Then people realized as the data grew, keeping everything in memory is very expensive. Why don't we actually offload some of it into the local disk? And with this, you can optimize the cost by 70% by having the data laid out on a local disk file system and then have the index in memory so you can ask the questions. And then that's where data warehouses came in, including Snowflake or Databricks, where they said, hey, what if we do this compute and storage isolation where we can take the data and put it on object storage and still keep run the compute on this dynamic cluster where you can shut it down whenever you want. And then by this, we can now scale even further the data, order of billions of rows, and run the queries up to 5 times cheaper. But is there anything that we can do further? Can we actually take the index and also store it on object storage and cut the cost another 2 times, and in total, if you look, by 10 times? This hasn't been possible before, but we make it work, and introducing Deep Lake version 4. And what it does, it actually brings 10 times faster ingestion, under a second queries for 250 million vectors, everything sitting on top of an object storage without any in-memory cache, with 25 Gbps streaming from the storage layer to the computing machines. And all this multimodal, simple, no cache, async, and concurrent. Now, let me give you, like, kind of try to ramp you up on AI search. How many of you built a RUG here? 1, 2, 3, 4, 5, 10. I guess we have more people here as well. How many of you done lexical search? Vector search? Hybrid search? Agentic search. There's a bunch of other acronyms I know, but I won't share here. But basically, if you think of this letter here, is that you start with simple lexical search. Think of this like an early version of Google where you type your keywords, and then you bring across all the data set the keyword matches and bring back the results. Later, what happened 2 years ago successfully, that large language model representation became so good that it started kind of outpacing the BM25 index, this embedded index for you that you use behind the scenes for the keyword search, and had semantic meaning inside that improved the results. And furthermore, you not only now have top 10 links, but also get this top 10 links and give this to an LLM and get a final answer. Then you now can build your compound systems, building the agentic search itself. And then you can use multiple kind of iterations to refine your search, maybe verify the result, maybe also run a text to SQL and bring the results. But where is this going all? And the next step, which is not yet, like, kind of is in research mode, is building end-to-end neural search systems. And think of the self-driving cars. Recently, Tesla replaced all their 300,000 lines of C++ code that does the planning on driving the car with a neural network. And what if you can do end-to-end neural network search altogether? So what is RUG? It's just a fancy name for enterprise search. You have a bunch of documents. You take these documents, parse them through an OCR pipeline, cut into small pieces, vectorize, store it in a vector database, pick any of your favorite vector database. Then whenever there's a query, you fetch the top 10 results, similar, bring them into the context, ask the query to the LLM, and get the answer. All this looks simple. Everyone, you did it at home. But a question here. how much complexity is it to build your own version of Google. Here's a recent research post by Mario, who actually went and studied Google and all the legal work they have done in the past to kind of reverse engineer what is the search engine complex system behind the scenes that they spend order of billions of dollars building themselves. And then since we are in developer system, like meetup today, I can actually deep dive on this architecture a bit. So on the left, you see, on the top left, you see the crawler that collects a lot of the data. It takes the kind of the lexical part, put that into an inverted index, which they call this word index here. And then they also crawl separately the images, put them into an image container, and all this looks great. And then whenever you run a query, it gives the top 1,000 results, and then brings to this like bunch of, is what they call Mustang, as like bunch of re-rankers, including DeepRank or RankBrain, that now use neural networks to be able to re-rank the top 10 results and bring it back to you. But also before bringing back to you, there's also this Twiddlers that they can build a lot of manual for this feature engineered kind of priorities or repriorities based on time of events, what's happening in the world, to kind of reprioritize what you see and personalize and eventually bring it back to your like Google search result, all this like in milliseconds. So like all these RAG builders, what do you think how much time it will take us to build this and how much infrastructure? It's a pretty complex system. But what I think is what happened recently is because of, thanks to the deep learning, is that there's a crack in the system whole the process. And what this can be actually replaced by end-to-end neural networks. And the system here, what we are proposing with AI Search with DeepLeak version 4, that actually can cut the cost by 10x, is running the search across multiple data sources, multiple clouds, multiple storages. But also this key last component, which I will go through the code in a bit, is that now you can take PDFs, instead of writing your own OCR pipeline, separating the images with text, you pass this through ColdPaly, which is another deep learning model that takes the image, gives a bag of representation, run the search, and bring back the final results into an LLM that can give you a summary. And one of the key things that we did is that we took this index from the compute layer and put it on object storage that can save the cost by up to 10 times when you run the queries. However, now you pay outside of latency cost, where instead of millisecond latency, you run the queries under a second. For real-time use cases, this is not great, but for data warehouse style or analyst style queries, this works pretty fine, especially the savings you have. But the problem here, going from an embedding to bag of embeddings, which is this dense representation of multimodal data that recently surpassed like this kind of classical pipelines, requires 30 times more storage. And you can actually trade off this 10x cost efficiency with 30x kind of the trade-off, and now get these multimodal capabilities to run search across all your data sources without writing all these manual pipelines. And now let's go through kind of the use case step-by-step building this. We just recently revamped our docs, so you can go to deeplake.ai to docs.deeplake.ai, and there's a RAG guide, and which guides you to go from building just a simple lexical search to running this multimodal deep lake search that I mentioned in a bit. Here you pip install deep lake, you load a data set, and this data set is a very simple data set with 18,000 restaurants. What we are doing here is just building the naive lexical search, very boring. We have this 18,000 restaurant menu items. We build this index and run the search. And what it is like very simple. You create a data set. It can run on your local file system, or it can run on your own S3 or managed by us. You create 3 columns: restaurant name, restaurant review, owner answer, and all of them you specify that, hey, I need an inverted index. What's happening behind the scenes, you load all the data, you add the data to the data set, nothing fancy, you get a data set object that now has an index, and what it can do, you can run a simple query here, which says, hey, select all where this restaurant review contains this word, and give me the top 4 results. And you get the answers. So far, so good. I think you have seen this all, nothing fancy. Now, what we are doing here is saying, okay, this is great, work it on local file system. What if I want to move this to actually to the object storage layer? So instead, the only difference you should do is when you create the data set, you point to your own S3, or you can also point to active loop storage, which redirects to your own cloud storage on Azure or GCS or on AWS. And then you can do the same operations, but now instead of inverted index, we use BM25 index and create a data set now that can do lexical search. But the biggest difference here is that the index itself is sitting or residing near the object storage, which later helps you with cutting a lot of cost efficiencies, getting a lot of cost efficiencies when you run at scale. So far, so good. So let's go to vector search. Now, as you have seen, BM25, super easy. Currently, we add OpenAI, add the embedding function or define it, add the OpenAI API keys. And what here we can do is we create the same data set, but now we have additional column, which is the embedding. And the embedding, we define the type. That here's the embedding. We use their latest version of embedding model using the large one, and now define the data set. And when you commit the data, which happens here, the index is automatically created behind the scenes. And now you have this table representation of the data set with 18,000 elements, and you can run both vector search and BM25 search at the same time on the same data. So here, we just define the type of the query we are running, define the query itself, and run just the vector search and get the top 10 results. And great, awesome, now we have the results. I think you have all seen this. I will not surprise you. Any of this, let's just skip. Okay, awesome. Now, how we can do hybrid search. Hybrid search is basically you run both queries at the same time, vector search and BM25 search, and then you fuse it. I think here's the vector search, here's the BM25 search. You run them separately. In this case, you get the final results for BM25 and vector search results. And the question is, what is the best way to fuse this? One naive way, you can take both scores, you sum them together, and great, you have a result. However, this approach is pretty bad because the way BM25 is doing the ranking process and returning the scores versus how vector search is working, they're very different. And BM25 is also very local. So if you just linearly sum them or with some coefficients, that's actually a pretty bad idea. What you can do, here, there's like a fusion you can define, which called, in this case, I use just softmax function. So we take the vector search scores, we apply the softmax function, and then the same kind of normalize the BM25 results. And then at the end of the day, we get these two results kind of merged together, which gives us the documents for both of those. Here's the merging, the fusion is happening here, where you take both the vector search, BM25, you normalize them, then apply some coefficients and sum them together, and great, you have now the final results returned to you. Okay, so far I hope I haven't yet surprised you. These are just standard methods. I think there's one thing interesting you can do with Deep Lake very easily is that what I've shown you, everything the Python code was running in sync mode, you can just swap it to async, and it makes it easier to bring it to your Flask or Fast API application behind the scenes. And then now you can run both BM25 and vector search in async mode, get the results, and bring it back down to your space. Okay, so I think the key interesting stuff happens here is that when we want not only to run the search across a bunch of text documents, but also images. How do we do this? So again, now with use Clip. Clip is deep learning model, I think a couple of years ago, that can both embed images and text together in the same embedding space. And the way it's trained, you have these image text pairs, you get the text encoder and image encoder, and then eventually you have a transformer that processes this data and gives you a vector representation. And you can use text vectors and search across image vectors, or you can use image vectors and then search across text data. And here we just use Torch and Clip to be able to load the model. Then the pre-processing function, we define the transformation that you have to do the images before you give it to the model. Now redefine the embedding function that can now process images on your own GPU and get the scraped already data set we have, but you can scrape yourself, image the data itself, and now define the data set. And now we have an additional column here, which is this types images, where we add, and also the embeddings that we collect from the images themselves. Awesome, bunch of boilerplate code, and here's the search. The same way as you run the vector search, you can also run on the images themselves, and finally get a result of here's the image query of burgers. We have a bunch of images inside the data set, run the query, and finally get a bunch of workers back. Okay, so far so good. I hopefully kind of ramped up you up to the what is happening inside the search for the last maybe 10 or 20 years. And recently, there's new models that will help is what they did. The key innovation here is the following, is that instead of taking a single vector from a text passage or let's say images, what if we go and take vector per each token? The density of the data becomes very high and becomes very complex to manage. But what it can help is we can actually increase the accuracy of the search and the representation itself. So Colbert, also done by Omar, so he took this approach, created this very dense representation of both queries and documents, and also defined this maxim operator where you can run a search across the text data. Currently, Colbert is mostly used as a re-ranker, so I wouldn't be kind of using this as for the main storage. But this gave this basis for building multimodal search without the OCR pipelines. And this is where ColPoly comes into the picture. Here we have now ColPoly, which is an extension of Colbert that can take the visual language model, the images, and give you this dense representation. And the biggest difference that you get is that now your OCR, the document itself, there's no any OCR pipeline used. The OCR pipeline has been replaced by a visual language model. And the good news is that only recently, a couple months ago, that the accuracy of the text search on ColPoly became almost equal as if you parsed this to a traditional classical OCR pipeline and get the vectors and then run the search. But additionally, what you can do, you can now also search across the figures or tables, which haven't been possible to do before. The advantage is that if, let's say, you wrote, you have, let's say, 1 million invoices that are coming to you, you have built your OCR pipeline that works, and then there's a new type of an invoice that comes. Now you have to build this additional use case, which is not possible. You have a question?
Isn't this much more expensive than OCR?
Depends. You'll have another set of deep learning models that are running behind the scenes for doing that. It's expensive in terms of the amount of the storage that it generates, but you also have a model that's about 2 billion or 3 billion execution that is the same as you run your embedding models. So it really depends on what kind of embedding model you use for the OCR pipeline. But you have an LLM here as well to process the data and get vectors. The only big, I think, difference that comes into the place is the amount of the storage that's generated in the middle layer, and that's about 30 times more. Okay, so here we load the visual language model, have the preprocessor pipeline ready, and then we define the data set. We get the images from the following scrape data set, define the columns. We have the image, the question, the embeddings, and then here everything is the same as I showed you before. And then now we append the data. And during this appending process, we take the images, give this to the model, we get the bag of embeddings or this matrix of embeddings, and then now we, instead of embedding as giving a single vector, now we give a bag of vectors per each image. And finally, what you can build is this kind of chat with images use case where first you get the query embedding given a question. You take this query embedding and give this now, instead of using vector search, you use this maxim operator and get the most top 10 relevant images in this case. And finally, after retrieving the top most similar images, which is here is a figure example, you can give this to a visual language model to process or analyze this to be able to answer a question for you. And here's a representation of, I think, using OpenAI GPT-4o Mini for processing the image that was retrieved from the Deep Lake dataset to bring it back to you. Finally, you get the image, and the answer was the question to it. Okay, how are we doing in terms of timing? We are getting there. So this is what I showed you now, is it actually the coding implementation of this left part, where you can go from lexical, like the naive search, to image vector search, to later bag of embeddings, and then combine this all together into your agentic iteration search to have like a Perplexity style answer engine. If there are 3 things I want you to remember about us, is that we are multimodal, we are 10x more efficient than any other database, and we are AI search ready, and this technology is already deployed in Fortune 500 enterprises across all major cloud providers. Thank you very much.
That's great. Thank you so much. I think we have time for maybe 2 questions, if they are quick. So who is interested? No one? Too technical? No, someone is here.
So you've mentioned about Colbert and Colpoly, I think, in the sort of like the late way in which it could possibly do chunking and could possibly sort of get the embeddings from multiple contexts. Is there a way to sort of define, like, I mean, would I have to like fine tune it for my specific enterprise use case? Or is there like right out of the box itself, like it sort of figures out what's better way of doing it?
Well, I think it's any other language model. It will work for generic use cases that has been trained on. But if you have very specific use cases, you have to go and fine tune it yourself. The best way is to check what Colpoly dataset has been trained on and see if your data that you use in enterprise is trained on this or not. And if not, you can actually take that and fine tune for your use case and improve it. I think you asked another question actually in the beginning, not just about the model distribution, but also how the Colpoly, I guess, works, right? And it's very similar. What we are going through is very similar to, like there's another technique you mentioned, which is late chunking. And what late chunking does is like, hey, instead of us feature engineering the first chunking process, what if we delay this later and then we can figure out the chunking after the embeddings are happening and then find the relevant chunk or the context. And what it all goes into is like, if you think of embedding a data, which is your perception model, and then you have this agentic iterations, which is your planning model in self-driving cars, and then they are now like manually feature engineered together. And then we are like kind of approaching this process where everything will be end-to-end neural network. And the way you're going to train these models is, hey, here are my question, here's my data set, here's my questions, and the labels and the answers. Can you actually fine-tune the whole end-to-end system to be able to answer this question? And as you go into get more data, as you go into more production, as you get more miles out of your system and cover all the edge cases, you will figure out, hey, fine-tuning every part will improve my overall accuracy. And this is what like Tesla Autopilot team is doing every day by collecting all the data and retraining their models and deploying them in production.
And are there like sort of, I mean, my data could be in images, my data could be in tables, databases, whatnot, right? Like, and I just ask it like a semantic question, and now it has to sort of identify what and where to pull from.
Yeah, I didn't talk much about this second part. This is how agentic iterations should be implemented. But yeah, so there's like, you should take a combination of text to SQL plus the vector search, lexical search. So you kind of use all this combo of techniques currently, but step by step, all this will be removed. And the hope or the vision is that everything will become end-to-end neural network where you no longer will need to be able to like manually feature engineer all these sub techniques. Not now, it will take us years. We were
It's a
promised.
great vision, it's definitely great.
We were promised self-driving cars like 5 years ago, so it will take time.
Hi. So I wanted to ask you, you had shown that it's currently being used by Fortune 500. So what kind of applications are, like, is it used mainly now, currently?
Yeah. So we have one of the, like Bayer, which is a life science pharma company. They have a lot of radiology images. We have Flagship Pioneering. They have a lot of scientific articles or do search on PubMed documents. We have Matterport as a customer using like what they do 3D reconstructions of real estate, wherever you go to Zillow or Redfin, whenever you do like this 3D virtual scenes, most likely it's them running behind the scenes. We help them to manage the data for training their GenAI models. So those are some of the use cases that Deep Lake is being currently used on. And we also have like startups, they like analyze all the YouTube videos, run search and bring back to be able to predict which video is going to go viral. And yeah, so that's like kind of specter is pretty big.
Cool. David, thank you. Let's
Thanks,
give
everyone.
David a round of applause.